Hi, this is a collision problem. This is an inelastic collision from Chapter 7. Pause for a moment and read the problem. So in any collision, and this is a collision, the total linear momentum is conserved as long as the impact forces are only internal forces, that is, between the car and the truck themselves. In this example, we know that there's also the road, which causes some force. But actually, if we just look at right before the crash and right after the crash, the internal forces of impact between the truck and car are far greater. They dominate anything that the friction on the road can generate. So as long as we just look right before and right after the collision, we can still use the conservation of linear momentum in this crash, and it's going to be true to a good approximation. If we wait too long, of course, eventually the car and truck that are stuck together are going to come to rest, and then in that case, the final momentum will be for the system 0. And so at that point, if you wait too long, you can't use the conservation linear momentum. But so let's go ahead and write this out here. So we're going to distinguish the two initial and final conditions as usual. So this is initial, before the crash, and this is final, after the crash. And we want to know what the velocities and the masses are of these things. So we're going to use the conservation mechanical energy, which says add up all the momentum in the beginning. And since momentum is approximately conserved here, when we add it up at the end, those numbers will be equal. What is our system here? Always need to figure out the object in our system. Well, there's only two things, right? There's the truck, and there's the car. So we need a linear momentum term for each. So let's go ahead and write this down. So in the beginning, we've got the mass of the truck times the velocity of the truck initial. There's the linear momentum of the truck in the beginning. And for the car, mass of the car times the velocity of the car in the beginning. Conservation of linear momentum says that will be the same when we add these together. We'll get the same number in the end. Oops, mass doesn't change. Don't need to put subscripts for mass. Final velocity of the truck. Final velocity of the car. And in this case, in part A, we're trying to find the speed of the entangled vehicles. In fact, look at this. Entangled means that these guys are stuck together. And that means that their speeds are both the same, right? This is the same speed for the truck at the end as it is for the car at the end. Since they're both stuck together, they move with the same velocity. I should be saying velocities here. And that allows us to simplify a little bit. If we take this side of the equation, I know that these are the same, so I might as well just cross out the truck and the car and just call this V final. And because it's the same, I can factor it out. So I'm going to end up with factor out my V final, the same velocity for both, and then I just have the mass of the truck plus the mass of the car. And I've still got the same equation on the other side, right? Now, if I want to go ahead and solve for V final, all I got to do is divide by the mass of the truck times the mass of the car. So V final, in this case, is going to be equal to this whole thing divided by this whole thing. Oops. And let's go ahead and plug our numbers in here. All right, so all of the masses and the initial velocities are given to us here in the problem statement. The mass of the truck, mass of the car, initial velocity of the truck, initial velocity of the car. Let's plug those numbers in. So for the truck, we've got 1,800 kilograms mass, and we have an initial velocity of plus 15 meters per second. For the car, we've got 900 kilograms of mass, and we've got an initial velocity, negative 15 meters per second. Again, these are velocities, so those plus or minus signs for direction are crucial. And in the bottom, we're going to sum the masses. 1,800 kilograms plus 900 kilograms. And then we need to effectively put those in the calculator and see what we get. Doing that, I come up with a final velocity for both the car and the truck, since they're stuck together in the end. That's what means inelastic collision, when they stick together. Get a value of plus 5 meters per second. And so that is the answer for part A. Now for part B, it says, what is the total kinetic energy lost by the car and truck during the accident? Well, in a inelastic collision, the kinetic energy is not conserved, so the total amount for the system before and after is different. In fact, you lose energy. In an elastic collision, the maximum amount of kinetic energy is lost. So to figure this out, let's do the KE total, or the sum of the KE for the system initial, and then we'll also calculate the sum of the KE final, and then they're asking us to look at the difference to see how much was lost. So initially we've got 1/2 times the mass of the truck times the speed of the truck. In this case, it is a speed initial, since kinetic energy, it only depends on speed. And then we have to add that for the other object in our system, the car. And so we'll plug those numbers in. So I've added the numbers there, and this term, when we plug that into our calculator, and this term, we plug it into our calculator, we get these values: 2.025 times 10 to the 5th joules for the truck, and smaller amount, 1.0125 times 10 to the 5th joules for the car. And adding those together, we get a total initial kinetic energy of 3.0375 times 10 to the 5th joules. I'm going to go ahead and calculate now for the kinetic energy final. In that case, it would be the same equation, right? The kinetic energy of the truck in the beginning, in the end, plus 1/2 mass the car times the car final speed. Again, we recall that these two are the same, right? We just already know because they're stuck together, so I can ignore the truck, I can ignore the car, and actually factor that out from the equation if we want. So that's going to be, let me factor out all the like terms. So we have a 1/2 m, sorry, got that wrong. We got a 1/2, which is common, and we got the speed term, which is common to both, right? And then I'm factoring out that, and I'm left with the mass of the truck plus the mass of the car, and I need to just plug those numbers in and calculate, right? So that's a 1/2 multiplied by 5 meters per second squared, and then the sum of the masses. And if we put those into the calculator, this is the number we get. It's a 0.3375 times 10 to the 5th joules. So notice that we've definitely lost some kinetic energy after the crash if we compare these two numbers. And of course the difference, how much was lost, we're going to go ahead and just subtract the final from the initial. And when we do that subtraction, so I'll just show it right over here. So the change in the total KE here, it's going to be KE final minus the total KE. Sorry, I got that backwards. The total initial minus the total end tells us how much we lost, and so that's going to be our initial 3.0375 times 10 to the 5th joules minus our final 0.3375 times 10 to the 5th joules, and when we calculate that, we get a number 2.75 times 10 to the 5th joules of kinetic energy were lost here in this crash. This is the lost total KE. Now, what happened to that energy? We know that energy globally, all forms of energy, is conserved. It's not lost. This energy was lost because the cars were dented. It took energy to rearrange the atoms in the materials. There was noise, and that noise carried energy away, and there was heat generated. So all of that lost kinetic energy was transferred out into those other forms of energy.